Now that we have a foundation built for the relationship between functions and inverse functions, we begin our study of a pair of very special inverse functions. They are exponential functions and logarithmic functions. All of the properties exhibited by inverse functions we can apply to exponential and logarithmic functions. In section 5.2, we'll study the first half of this pair, exponential functions, and then in 5.3, we'll look at the second half of the pair, which is logarithmic functions. Now, let's begin by reviewing some rules of exponents in section 5.2.1. We're going to go through this rather quickly because this is probably a review, but if you're a little rusty on these rules, I hope this part is helpful. To begin with, let's look at the rule for a zero exponent. A to the 0th power equals 1. So any base raised to the 0th power is equal to 1. For example, on my calculator, if I raise 8 to the 0th power, the output is 1. So we can describe this mathematical rule in words as follows. Any base raised to the 0th power equals 1. When you see that expression, you may be tempted to say a to the 0th power is equal to 0, but make sure you understand that is exponentiation, not multiplication. The next rule deals with negative exponents. If I have a negative exponent applied to some base, then I can move that expression to the opposite place in the fraction and change the sign of the exponent. That applies if I have a negative exponent in the denominator as well. A raised to the negative n requires two changes. I'm going to take that expression to the opposite place in the fraction, which is the numerator in this case, and change the sign of the exponent. So remember it this way. To evaluate a negative exponent, we're going to make two changes. Move the expression to the opposite place in the fraction and change the sign of the exponent. So if the negative exponent is in a numerator, I move the expression to the denominator and change the sign of the exponent, and vice versa. If the negative exponent is in the denominator, I move the entire expression into a numerator and change the sign of the exponent. The next three have to do with applying operations to exponential expressions. For example, a to the mth power times a to the nth power is equal to a to the m plus n power. In words, we can say when multiplying like bases, add the exponents. Again, this is likely a review, but I do want you to notice one thing that will help prepare you for the way this is going to look with logarithms. Notice here I've got multiplication between the bases. By the way, the bases are the a's, the number there on the baseline. The exponents are m and n. So I have multiplication between the bases, and I'm converting this into addition in a different location, right? So the multiplication between the bases becomes addition between the exponents. Again, we'll see that same translation when we apply it to logarithmic functions. If when we're multiplying like bases, we add the exponents, then it makes sense that when we are dividing like bases, we subtract the exponents. In words, we can say when dividing like bases, subtract the exponents. So multiplication and addition go together, division and subtraction go together. The next rule is called the power rule, and it has to do with successive exponents. If I take a base a and raise it to the nth power, and then raise that to the nth power, then we can simplify it by multiplying the powers. In words, when raising a power to a power, multiply the powers. Make sure you see when do I multiply exponents and when do I sum exponents. We've got two related rules here, this one and this one, right? Notice on the product rule I have two separate bases. The multiplication occurs between the bases, so I add the exponents. In this case, I have a single base and I have multiple exponents. So in the case of successive exponents, we want to multiply the exponents. These three rules will appear in logarithmic form in the next section. So make sure you have a good understanding of those three basic rules. Next, we're going to look at how to simplify a product and a quotient raised to a power. If I have a product, a times b raised to a power, then ultimately I can distribute the exponent to each factor in the product. A to the nth times b to the nth. So we can say each factor, or let me say it this way, sorry about that. When raising a product to a power, distribute the power to each factor in the product. Notice how many words it takes me to explain this one concise formula. Mathematics is a very efficient and dense language. It's short and sweet, and sometimes it takes a lot of words to really understand what those formulas mean. In the same way, when we have a quotient raised to a power, each part of the quotient receives that power. So to describe our quotient rule, or quotients to a power, we can say when raising a quotient to a power, distribute the exponent to the numerator and denominator. In each of those explanations, I used the word distribute. One thing that I want you to watch out for, we'll say caution, is that we cannot distribute an exponent across a sum or a difference. So if I have something like a plus b to the nth power, we cannot distribute the exponent across that plus. We can distribute it to each factor in a product, or to each part of a fraction. But if you are adding or subtracting and you're raising that sum or difference to a power, then we cannot distribute the exponent across a sum or a difference. A perfect example of this, if we look at x plus 2 squared, this is not equal to x squared plus 4, right? If we have x plus 2 squared, that would be evaluated as x plus 2 times x plus 2, and when we carry out and simplify the FOIL, we'd end up with x squared plus 4x plus 4. So notice whenever I distribute the exponent, I would be missing information. I'd be missing that middle term. So you can distribute an exponent across a product or a quotient, but not across a sum or a difference. So make sure you know that subtle little difference. Now, let's practice applying these rules. In example 1, we are going to simplify using positive exponents only. So if we end up with something with a negative exponent, we're going to evaluate it and simplify it. Example 1, notice we are multiplying like bases. The rule that we looked at only had two factors or two bases. We had a to the m times a to the n, and we added the exponents there. But that rule can be generalized to any number of factors in the product. So we can say here we're multiplying like bases. We're going to add all of the exponents, and we end up with 2 to the 8th power. Let's go ahead and evaluate that with our calculator. To simplify, we would end up with 256. Example B, we have 5 raised to the negative 2 power. Remember, when we have a negative exponent, we make 2 changes. We're going to move the entire expression to the opposite place in the fraction and make that exponent positive. So 5 to the negative 2 is a short and concise way of expressing the fraction 1 over 5 squared, or 1 over 25. Now remember, when there's numbers like this, you can check every single one of those with your calculator. So I'm going to evaluate 5 to the negative 2, and I'm going to go ahead and do, 5 to the negative 2, and let me just evaluate that. 0.04, and then I'm going to convert it back into a fraction to get 1 over 25. So I can verify anything that has arithmetic with my calculator. Example C is related. Notice the negative exponent in this case is in the denominator. So I'm going to take it out of the denominator and put it into the numerator and change the sign. Now, if you want to write it like this to be very clear what happened, it moved to a numerator, and then you can simplify like so. So 1 over 5 to the negative 2 gives us 25. We can verify that very easily with our calculator. And we get the same answer. Example D, notice we have a quotient raised to a power. So each part of that quotient will receive that exponent. So I'm going to distribute the exponent to the numerator and the denominator. 1 to the 3rd is 1 times 1 times 1, or 1. And 5 to the 3rd, 5 times 5 is 25, times another 5 gives us 125. So 1 over 125. We can begin example E in a similar way. We're going to raise each part of that fraction to the negative 3rd exponent. So I've distributed the exponent to each part. And then, since each part has a negative exponent, each part needs to move to the opposite place in the fraction. So the 5 to the negative 3 moves up to the numerator, 1 to the 3rd moves down to the denominator. Then we can evaluate. 5 cubed is 125, 1 cubed is 1, so we end up with 125. Now, we're going to run into a fraction raised to a negative exponent quite a bit, so let me show you a different approach that may be a little more efficient. 1/5 to the negative 3, notice we ended up switching the positions of our numerator and our denominator. So one thing we can do here is go ahead and switch the positions, and when I do that, that changes the sign of the exponent. 5 over 1 is equal to 5, and then I can raise that to the 3rd power, and we get to our answer just a little bit quicker. Either way you do it is correct, but again, if you have a fraction raised to a negative exponent, it's really easy to invert that fraction and then exponentiate. On example F, we are going to simplify our numerator first. Notice in the numerator we're multiplying like bases, so we need to add the exponents. And when we simplify there, we get 3 to the 5th over 3 to the negative 1. Now, we need to take the expression with the negative exponent out of the denominator and move it up into the numerator. It's going to join the 3 to the 5th that's already there, and we get 3 to the 1st power. Then we are multiplying like bases, so we should add the exponents. We get 3 to the 5 plus 1, or 3 to the 6th, and let's go ahead and evaluate that to end up with, looks like 729. So those are pretty straightforward applications of those rules because they involve numbers, but let's see if we can apply those rules to expressions with variables. In example 2, we're going to simplify the algebraic expressions using our new exponential rules and express the results with positive exponents only. So on example A, the first thing I'm going to do is take care of, actually, let's do this. There's several ways we could go here. Let's observe that we are multiplying like bases in the denominator, so we can go ahead and add the exponents. 3 plus -1 gives us 2. Now we are dividing like bases, so we can subtract the exponents. 5 minus 2 gives us n to the third power. So our simplification here is n to the third power. If you had moved that n to the -1 up first, combined the n's in the top, and then applied your quotient rule, you'd end up in exactly the same place. So the order of these rules doesn't matter. It just matters that you apply them correctly. On example B, notice we have the situation of a fraction raised to a negative exponent. So let's go ahead and invert that fraction and change the sign of the exponent. That's what we were talking about doing up here on example E. Makes it really efficient and clears the negative exponent pretty quickly. Now, we have a quotient raised to a power, so each part of the quotient is going to receive that exponent. So we are distributing the outside exponent to the numerator and to the denominator. Now we're in the situation of successive exponents. I have a power raised to a power. Now remember, when you're multiplying like bases, when you have distinct bases, you add the exponents. But when you have successive powers, a power to a power, we multiply the powers. So in this case, on the top, we're going to multiply these two powers to get y to the 10th. And in the bottom, we're going to multiply those two powers to get x to the 4th. Now, the result has positive exponents, and everything has been combined and simplified. I don't have multiple x's to combine or multiple y's, so we are finished. Example C. We see a product raised to a power, and notice right here we have q to the 0th power. That catches my eye first. Remember, anything raised to the 0th power is equal to 1. So that is really just a 1 right there. Let's write the expression without the 1, because that expression times 1 is the same thing as r cubed times s to the -2. Next, let's evaluate our negative exponent by moving it to the denominator. Now, when I move it to the denominator, I have to recognize it's still under this outside power. So I'm going to keep my parentheses. The s squared is moving to the opposite place in the fraction, and I'm changing the sign of the exponent. Then we're back to our situation we had on example B. We can go ahead and distribute that outside exponent to each part of the fraction. And then we realize we're raising successive powers in both the numerator and the denominator. So we can multiply the powers on the top to get r to the 15th, multiply the powers on the bottom to get s to the 10th. There are no negative exponents. Everything's been completely simplified, so we know that we are finished with that problem. All right, I hope that was a sufficient rule of rules for exponents, and soon we will talk about exponential functions.